Okay, here we go. We'll talk basically about different types of digital modulation. This is kind of a short one. About keying defects when you're basically doing CW, because what you're doing is kind of using a square wave to modulate the carrier. And as you remember, square waves made up of all the odd harmonics. So by definition, you're creating spurious emissions. So we'll talk about a couple things you do to kind of reduce that. Some of the digital codes that are used, a little bit about spread spectrum, which you probably use every day. That's what your cell phone uses. Or at least one of the forms. So key clicks are what they call them when you send CW and you hear the kind of clicking sound sometimes. Kind of the recommended method is to adjust the rise and fall times, and a lot of radios will let you do that. So actually, instead of a square wave, you're making it more of a trapezoidal type, which cuts down on the amount of harmonics. The ARL recommends the 5 millisecond rise and fall times. And there's what the normal square wave would look like. And then if you do a 5 millisecond slope on both ends, then you get this more, I did say trapezoidal, more triangular. There's also a raised sine that some radios use, and you can see that's the red line. So it's actually part of a sine wave that's clipped off. So it actually gives you a little more rounding here at this edge and helps reduce it. And not all radios can do that, but they should be able to, at least on a base station, to adjust the rise and fall time. So what's the primary effect of extremely short rise or fall time on a CW signal?
Sure. Charlie.
What's the most common method of reducing key clicks?
Charlie. No, increase. Alpha.
Huh?
It was. Okay, I read it too fast. It jumps in. There's a lot of them like that. It's real easy to just see.
Yes, yeah, like to mentally justify it, and then you're like, wait a second, that was.
Yeah. That's why you should always read all four.
Yeah.
Because I fall into that trap a lot if you're in a hurry.
Yeah.
Because it's increase or reduce.
Yes,
and
yes.
Big difference.
Yes.
They do some tricky questions like that on purpose. Some of the digital modes like FT8, I don't know why they brought up PSK, because it's not audio frequency shift, it's phase shift. In either case, you have to set the audio level from your computer, right? Or you're going to basically overmodulate and cause a lot of harmonics. And one of the things you're supposed to do is measure how much intermodulation distortion you have in the signal. In order to do that, you really need to look at it with a spectrum analyzer. And it's not something you're going to see on most radios. So what's a common cause of overmodulation on audio frequency shift keying signals?
Delta.
What parameter evaluates distortion of an audio frequency shift key signal caused by excessive input audio levels?
Delta.
No. I just threw this one in just so you know it, because if you remember, was that one question where you actually had to calculate one. No. The main one here is what they call an idling PSK signal. The IMD level should be minus 30 dB or better. And our internet is unstable, I know that. I had a hard time getting connected. What is considered an acceptable maximum IMD level for an idling PSK signal?
Delta.
Some of these they make awful obvious too, you know, like that one. It's like,
That's what I said. I think the extra, in some ways, is easier because you've got a lot of questions like that. Even the ones you have to remember. I mean, they're
Well, how's that obvious?
because the other ones are gain. You're seeing gain.
they're positive.
Okay, so then the negative is,
It's less.
Way down. It's
okay,
you don't
Minus
plug-
dB is less than 1.
okay. Yeah, there's a whole way of thinking on this.
Remember, 30 dB down is SPI pounds.
What's it? Wave.
Every 10 dB is 10 times. Vice versa. If it's 10 dB down, it's a tenth. So what do you think? 1,000 is 10 times 10 or times 10.
I see. Okay,
So if you remember the formula for dB,
yes,
it's 10 times the log ratio. So the log of 10 is 1, which multiplied by 10. The log of 100 is 20, I mean, it's 2, so you multiply it by 10, and so on.
okay,
Because they threw the 10 in there to make it a decibel instead of a bell. It's a long story with AT&T, and that's a long time ago.
interesting.
That's why we're set. Digital codes. ASCII is, I would say, probably used more than any. Well, there's also a Unicode version of it. I think the first one was Baudot code, which they use on teletype machines and radio teletype, and the RTTY mode still uses Baudot code, which is a 5-bit code. So you get 5 data bits for every character or symbol. But it can only do lowercase. So you have to actually do 2 characters to do a shift, to do an uppercase or one of the specials. Where ASCII is 7 or 8 bits, depending whether you include parity. 7 bits plus or minus parity. And it covers the uppercase, lowercase, and special symbols. This is a sample of what, it's hard to read, but it's actually from the patent from Mr. Baudot, how he did the code. So he's got pluses and minuses instead of 1s and 0s. And notice that was 1888.
That's incredible.
This is the ASCII code. It's actually showing it in hexadecimal. It's another one for you. Hexadecimal means you're doing 4 bits at a time.
It's base 16.
It's what?
Base 16 counting instead of base 10.
Okay,
So you go 0 through F.
okay,
You're at F1, F2, F3, all the way to F.
okay.
Yeah.
So what are some of the differences between the Baudot digital code and ASCII? See, what's the deal on this one? The longest one is right?
You're
Too long. How long each?
Yeah, I think this one it could be confusing. I think for me, because you got ASCII's 7 or 8 and like, so you're, but the 5-bit.
Yeah, there's only one that says 5, right?
So that's the problem.
Well, thank you for talking through that. That helps, you know. You're talking,
Because if you know, ask you 7 to 8, it doesn't, you don't,
yeah,
that's a simple answer.
yeah.
So normally that's what I do, but I don't know one thing, I try to find the other thing I know.
So what's one advantage of using the ASCII code for data communications?
Challenge.
C, it is possible to transmit upper and lowercase text.
That's correct. What's the advantage of including parity bits in ASCII characters?
Thumbs up.
Don't.
That's what kind of potentially throw you off on the previous question because it does.
But it's not correction, it's detection.
Yeah,
It can only say there's an error.
Right, because that's the way, that's what like great calls for business. Like there's an error in transmission, you know, just recently.
That's called ARQ. What's the, oh. Okay, spread spectrum is actually developed by the military to be more secure. Like it's extremely hard to jam it or basically decode it if you don't know the coding sequence. And there's 2 types. There's frequency hopping, and then there's direct. I think it talks about those a little bit more. According to the latest Part 97 that I looked at, it says 220 and above. In the previous question pool, it was 440 and above. I'm not sure if that was a mistake or the FCC changed the rule.
I know that there was somewhere I was looking, it actually had the whole question. So I think when they were updating stuff and it changed over, somebody must look at it, same question, but the answer that.
So the one type is frequency hopping, and they divide up the band that they use up on the ISM2, which is, I forgot what the I was, something service and medical, but it's a kind of up grabs band that everybody uses. Nobody is primary. So they divide that up into 79 1 megahertz channels, and then they use a pseudo-random sequence of 22 different channels and go through that sequence at around 2.5 hops per second. So it's changing frequency based on this pseudo-random sequence that when you like bind with it, you're both ends are using the same sequence, and nobody else is supposed to know that sequence because it is kind of random.
And change that sequencing periodically, and that really screws it.
Right.
Makes it hard.
So unless you have the sequence, you're really not going to be able to decode it. And it also, I don't believe there's a question, but uses what's called Gaussian frequency shift keying, just to throw in another big name. Whereas direct sequence, they use what's called this 11-bit Barker sequence. And they use that to actually modulate the carrier. So you're putting out different frequencies at the same time. So you're actually putting out these different patterns, which represent symbols for each one of the, well, for each symbol. So I don't know which one is better. I think the cell phones probably use frequency hopping, but I'm not really sure. I believe model RC uses direct sequence.
So that's for kind of encrypting.
No, it's not encrypting. What it does is it makes it harder to, if you are tuning in on a frequency, you don't know the sequence in which frequency hops current.
Okay.
So it makes it more difficult to intercept, and it also makes it more difficult to jam because you have to, unless, because if you're putting out energy on a frequency, it's a lot less energy you can put out on a bunch of frequencies. So.
But that's one of the reasons why it's only in the higher frequencies, because the bandwidth is so wide,
I see.
because you're putting out spread spectrum.
Okay.
Bob,
Yes,
one quick question. That previous slide about the spread spectrum, does that apply generically? In other words, to say wireless phones and the military and amateur radio? Is that generic?
yes, and they use either of those two modes.
I'm not sure I understand. It looks like there's only, in other words, spread spectrum is a mode, correct?
Right. There's two subtypes. There's frequency
Oh,
hopping
oh.
and direct sequence.
Okay, thank you. And so frequency hopping is the military.
I'm not sure which one the military uses. Probably both.
Okay, all right, thank you.
You mentioned the Barker code, and this is the 11-bit sequence that you go through to do the direct modulation. So it's a combination of either, instead of ones and zeros, it's plus and minus ones. So it's really doing phase shift. You're either doing a positive phase shift or a negative phase shift. It's a -1 because it's binary phase shift keying. Which describes spread spectrum frequency hopping.
So
Yes.
Yeah.
What spread spectrum communications technique uses a high-speed binary bit stream to shift the phase of an RF carrier?
it's a two-word sequence to me. Well,
Okay, now that one I have trouble with because maybe I don't know what it's saying that makes it differentiate.
Well,
so
this is, I'm sorry, go ahead.
No, go ahead.
Well, you originally said Barker codes, and this is not including that as an answer.
Well, a lot of these questions, the answers they give you will be a subset of correct things.
It's a futurity.
Well, let's see what it is.
No.
Correct sequence.
it's either frequency hopping, which is used pseudo-random frequency,
Right.
or direct sequence.
So that's what I was having trouble with, but then it says binary bit stream, so that's.
That's a good distract. That is a good distract. Because it is shifting the phase. Either positive, negative, so it is kind of binary, you know what I mean?
Right.
That's not the technique, that's,
So it makes you know that it's direct sequence.
Well, I guess because they asked for the technique
Okay.
as opposed to the actual type of modulation, which would be binary phase shift.
Okay, yeah,
But the technique is direct sequence as opposed to frequency hop.
okay.
Okay. They're more resistant. People can't decode it if they don't know the Barker code or the sequence. I guess frequency hopping, because of the width of the spectrum, I think is why this is going to be more resistant to narrowband because it's so much wider, where you get a higher data rate with direct sequence. So I think, I'm guessing, just a pure guess, that the military uses probably both of them depending on the application. Whether they want, less interference or they want to get more distance, which you can get, and you can send more data on direct sequence. But the key is any signals that aren't using this the correct algorithm are going to be rejected and basically ignored. Why are received spread spectrum signals resistant to interference?
I'm saying delta.
No.
I'd go with delta as well.
Record.
Yeah, I mean, I was just reading through all of them. I would have to study it a bit, but my first sense.
Dinner, chicken dinner.
There we go.
because it's not looking for interference. Thing is that it changes its frequencies.
Yeah.
And the receiver doesn't talk back to the transmitter. It's not like an ARQ type.
And that's the key thing in the question. The receive, it says wire receive.
See, I told you that was an easy one.
Problem is, all of these aren't too bad, but there's so many of them.
That's the difference. The 50 instead of 35.
Well, it's not even that, it's the 600.
Yeah, and still at like maybe 97% seen. I've been doing this every single day after work. Been seeing and looking at different questions. That's cool.
Are you used campsite.org? I think that's way to
Oh, absolutely.
as we go through there.